Dear participants, did you hear me?
Yes.
Dear participants, do you hear me?
Yes, we can do.
I'm sorry that Dr. Yüzbaşıoğlu and Dr. Tripathi, I think, join with us. And we will wait a little bit for the first presentation. Okay, we are sorry about this 5 minutes waiting. I think a little bit wait for the participants, and if they not join with us, we will start with Dr. Mukta Tripathi of her precious presentation. However, I want to wait 1 or 2 minutes more.
Hello, good morning, Professor. I'm Dr. Mukta Tripathi.
Yes, I'm sorry, Doctor. I will talk about opening speech, and then I will give the speaker to you. Okay, dear participants, welcome to the last day of our conference at Ankara Hall. First of all, thank you very much. I'm sorry. I'm so sorry that I want to record this conference. Okay. Now, just we talk about our conference, the last day at Ankara Hall. Thank you very much. First of all, thank you very much for your attention. My name is Tarık Asar. I am an associate professor at Gazi University Physics Department. And we have today this section 6 speech, 6 wonderful speech. And first, I want to ask you that, Dr. Mukta, I want to talk about your permission of your presentation recording and broadcasting to Zoom and YouTube. Is it okay for you?
Sir, you can play my video. Actually,
Yes.
I have already submitted there So I am comfortable if you can play that video.
Okay. Thank you. Thank you very much.
Thank you.
And I want to you that join with us with the questions and suggestions section of the end of the video. Okay.
Sure, sure, sir. Thank you.
Okay. I wait 1 minute. Sorry. Okay, we start the precious presentation of Dr. Mukta.
So very good morning to all of you. I'm Dr. Mukta Tripathi and I'm going to present my presentation, and this is the ICMAC 2020 which is held in 2 to 4 October 2020 at Gazi University of Ankara, Turkey. So the topic of my talk is fabrication of electrochemical characterization and electrochemical double layer capacitor using biomass P cover based activated carbon electrode for the improved performance. So let us see the outline. These are the outlines and they will explain the introductive part as well as the experimental technique and result discussion and the conclusion. So if we consider the introduction, nowadays the electrochemical devices are used too much, and due to its major applications such as the gadgets, some mobile phones, and the transportation, there is a lot of role of the electrical energy storage devices. So electrical vehicle is one of them. A part of this, we are considering the electrical vehicle in this particular way. This is the energy and power density plot shown here, and you can see the supercapacitors covered a large area compared to other devices, and this is due to that supercapacitor have a higher quality to accelerate and decelerate that particular vehicle, and it is used to braking of the hydrogen vehicle. So this is the that increase the peak power requirement to increase the efficiency and the life cycle. So what exactly supercapacitor? The supercapacitor has various properties such as it have a higher capacitance value compared to the other conventional electrolyte. So that is the main thing. Another thing is that capacitor have a high power source compared to the rechargeable battery and the conventional electrolyte. However, the specific power is also greater than battery, and its life cycle is also greater than battery. Compared to the conventional capacitor, the specific energy density is higher than the supercapacitor. So let us discuss the experimental technique. A part of experimental technique, first of all, we have synthesized biomass-based activated carbon. For this purpose, we have chosen the raw material, that is the P cover. So you can see here, these are the steps which is shown in this particular slide. First step is that we have chosen the P outer cover for the raw material, and that raw material has been dried using sunlight. After 1 or 2 weeks, we get the very dry form of that pea cover. Then after we will crust it and make it in powder form. After that, we kept it in a muffin furnace for the carbonization. So carbonization has been done by maintaining the temperature 500 degrees Celsius, and it is maintained for 2 hours. Then after we'll get that particular material is cooled for 12 hours. After that we get the powder form of the carbon. So this is the carbon powder, not an activated form. So that carbon powder has been again activated by using the your tubular furnace. So in tubular furnace we have maintained 800 degrees Celsius temperature for 2 hours. We have set up the program, and by using the nitrogen flow, that is 150 ml per minute. So after 2 hours it is cooled by using nitrogen flow for still 12 hours. Then after we get the powder form that will be washed with particular setup, and we use double distilled water. And before that we for the particular activation process we use the HCl solution for 5 molar concentration, and then after we will wash it thoroughly by double distilled water, and we get still we get that particular carbon material, and that will be dried by using the vacuum oven, and by maintaining 100 degrees Celsius for 12 hours we get the electrode material, as you can see in this particular diagram. So that is our electrode material. That electrode material has been pasted in the graphite sheet, and then after we will get that particular electrode material. So these are the techniques for the synthesis of the electrolytes as well as the electrode. So that electrode, what we have discussed previously, that electrode material has been pasted in graphite sheet. This is the process. You can see the preparation of the electrode material. Okay, so activated carbon has been, we have chosen PVDF HFP, and that activated carbon by maintaining ratio 1:9. After that we will mixed it thoroughly for 2 hours and 60 degrees Celsius. Then after we get the slurry, that slurry has been placed previously, that electrode that will be kept, that has been kept in 70 degrees Celsius for 2 hours. Then after we'll get the fine film of the electrode. So this is the preparation of the electrode material. However, this one is your electrolyte material. For electrolyte material, we use the solution cast technique, and these are the material we have used: PVDF HFP, polymer, TABF4 as a salt, acetone and acetonite as a solvent, and activated carbon as we have synthesized in our laboratory, and nanofiller, that is SiO2. Let's see the discussion related to that. So for supercapacitor analysis, we used three type of the technique, that is the impedance spectroscopy, cyclic voltammetry, as well as the charge discharge. So cyclic voltammetry and the charge discharge we will discuss here. This is the impedance spectroscopy. So in the part of this we used the cell, and the P based electrode, biomass based electrode has been sandwiched with the electrolyte system, which is the nanocomposite polymer electrolyte, and that combination of the fabricated cell has been further utilized as a analysis. So impedance for this purpose, you can see this is the impedance plot, and here these are the parameter we obtained from it. So here the bulk resistance as well as charge transfer resistance, and at 1 millihertz that particular capacitance has been obtained, that is 347.9 millifarad per centimeter square, as well as in the form of the mass, that is 144.9. So that capacitance has been calculated by using this formula. Let's see this particular experimental data has been fitted by using size Z view plot. So by this we found that the Berger impedance, and that has been calculated by using the equation which is shown here by equation number 2, and you can see there is good matching with the experimental and the theoretical data, and that equivalent circuit has been also shown in this particular particular diagram too. So this is the simulated electrochemical impedance spectra, and which is obtained by 1 millihertz and fabricated shells. So these are the parameter. You can see that RB is matched with the experimental technique. So that is the impedance. Let us see the cyclic voltammetry study. Apart of this, you can see these are two type of the plots from obtained from the cyclic voltammetry. Figure 3 show you the cyclic voltammeter for the P based shell, and that is the different scan rate. That is the plot for the CV you can see here, and the capacitance versus scan rate has been also shown here. So you can see approximately 228 farad per gram has been obtained at 1 milliampere, 1 millivolt per second scan rate. So here you can see from the cyclic voltammetry also we obtained the cyclic stability approximately 2000 from 0 to 2000 from one cycle to 2000 cycle. Overall the number of the cycle per number of the cycle, the capacitance is approximately equal. So this is the stability. It have a good stability. Now the next is your charge discharge analysis. So part of this you can see the charge discharge technique has been shown. Ideal rectangular shape has been obtained by this, and we get the energy density approximately 5.9 watt hours per kg, as well as the power density approximately 1.1 kilowatt per kg. So this is the achievement from our work. Let us see the conclusion about that particular conclusion. If we are considering, we are getting the higher capacitance, that is the 456.18 millifarad per centimeter square, as well as the specific capacitance has been obtained by the CV analysis at 1 millivolt per second scan rate, that is 228 farad per gram. So from the charge discharge technique, overall the rectangular shape has been obtained, and our fabricated carbon which we have synthesized, the cell show the good result, and the energy density and the power density has been observed by the charge discharge technique, that will be also good. Okay, so that is the value, and the value and energy density, power density show the improved performance. So this is all about, these are the reference. Thank you so much.
Okay, dear participants, do you hear me? Thank you very much, Dr. Mukta Tripathi. Thank you very much for a nice presentation. And now, do you have any question or suggestion for this nice presentation, dear participants? Is there any question or suggestion about this nice presentation? Okay. Do you hear me, Dr. Mukta Tripathi?
Yeah, Professor, I am here.
Okay. I want to ask you that maybe for the students is more helpful. Figure 6, you have a rectangular shape of this graph. Why this is important? As you say in conclusion, it's important. Why it's important?
Yeah, in figure 6.
In figure 6, yeah.
Yeah.
Wait a minute, maybe.
Maybe this is the cyclic voltammetry. Okay.
Okay.
Yeah, so we get the rectangular shape, and we are not getting any type of the peak. This show that we have a very linear plot, and there is no any redox reaction. A part of this, the area CV analysis is basically based on the area. So if you can see the CV, okay, so in CV that is affected by the area. So if you have a rectangular shape and that good area, we will calculate the capacitance is good. So there is a lot of study related to that. If that is due to that concern, we are getting the good rectangular shape for the CV analysis.
Okay, thank you very much, Doctor. And thank you very much for this nice and precious presentation. And the next speech, I check the.
Thank you so much, Professor.
Thank you very much. Thank you very much. I see that Anush Kumar, Mr. Anush Kumar is here. And do you have the presentation, Mr. Kumar?
No, I don't have presentation. Actually, I am the co-author with Dr. Mukta Tripathi.
Okay, thank you. Thank you very much for your attention about our conference. Thank you very much, Mr. Kumar.
Thank you.
Okay, I'm sorry that I wait about the presentation speakers. I see that. I'm sorry. I'm so sorry. And we are waiting the speakers. Okay. I think a little bit wait for the speakers of the presentations. Okay, I'm waiting for the presenters of the 5 presentation. We have more 5 presentations, and I will wait a little bit more and then start the videos of the other participants. Okay. 1 minute more, and then we will start the presentation videos. Okay, I wait 1 minute, and I will start the new presentation about the preparation of aqueous hybrid nanofluids and thermal system applications. Is belong to Erdem Çiftçi, and I will start the presentation video. Okay. Okay.
Erdem Çiftçi. I'm from Turkey and I'm a research assistant at Gazi University Energy Systems Engineering Department. It is great pleasure to me to present our study entitled Preparation of Aqueous Iron Copper Oxide, Zinc Oxide Alumina and Copper Oxide Alumina Hybrid Nanofluids and Thermal System Applications. My presentation content will be as shown. First of all, I will give some information regarding nanofluids and utilized material and methodology. Then I will tell our experimental study. At last, I'm going to mention about the findings obtained from the experiments. Nanofluid suspensions are the colloidal engineered nanoparticles containing working fluids. Although they improve the transfer capability of a system they use, their some thermophysical properties sometimes can restrict the utilization of them. The metal oxides have high thermal conductivity values and hence are likely to enhance the base fluid's thermal conductivity.
I'm so sorry that we will start the presentation again. I'm sorry.
On advanced materials science and engineering and high-tech device applications. My name is Erdem Çiftçi. I'm from Turkey and I'm a research assistant at Gazi University Energy Systems Engineering Department. It is great pleasure to me to present our study entitled Preparation of Aqueous Iron Copper Oxide, Zinc Oxide Alumina and Copper Oxide Alumina Hybrid Nanofluids and Thermal System Applications. My presentation content will be as shown. First of all, I will give some information regarding nanofluids and utilized material and methodology. Then I will tell our experimental study. At last, I'm going to mention about the findings obtained from the experiments. Nanofluid suspensions are the colloidal engineered nanoparticles containing working fluids. Although they improve the transfer capability of a system they use, their some thermophysical properties sometimes can restrict the utilization of them. The metal oxides have high thermal conductivity values and hence are likely to enhance the base fluid's thermal conductivity. However, they are not stable in a colloidal suspension. Similarly, metals provide stability when they are used in nanofluid preparation, but their thermal conductivity is lower than their metal oxide counterparts. In this aspect, the hybrid utilization of both nanoparticles have emerged in recent years, and many investigators reported that hybrid nanofluids can be utilized as a working fluid for performance improvement in a thermal system. In this aspect, we prepared and tested the ionized water-based hybrid nanofluids of iron copper oxide, zinc oxide alumina, and copper oxide alumina nanoparticles in a wickless heat pipe, air-to-air heat recovery unit, and tubular heat exchanger respectively. The changes in efficiency of the heat pipe and air-to-air heat recovery units and the overall heat transfer coefficient of the heat exchanger were investigated. Some properties of the nanoparticles used in the experiments can be seen in this table. Hybrid nanofluid suspensions were prepared by mixing the nanoparticles with deionized water and Triton X100 surfactant. During this process, the nanoparticle concentration was kept constant as 50-50. After preparing the nanofluid suspension, each was kept in an ultrasonic bath for nearly 3 hours to obtain more homogeneous and stable nanofluid suspensions. The experiments were performed 3 times, both for the ionized water and prepared nanofluid suspensions, and the average values are used in theoretical calculations. Each experiment was performed thrice, and the average values of them were used in the theoretical analysis. Schematics of the test rigs used in the experiments can be seen in this figures. As you can see, the wickless heat pipe was made of copper and it has 13 mm inner diameter. The experimental setup of the air-to-air heat recovery units contains 2 confined air channels for cold and hot fluid passages in the length of 1300 mm, a heat pipe bundle, and 2 air fans. The tubular heat exchanger, besides with the heat transfer area of 250 centimeter per square was used in the experiments. Heat pipe experiments were conducted under 300 watt heating power applied to the evaporator section and 7.5 and 10 gram per second cooling water mass flow rate conditions using iron copper oxide hybrid nanofluid. The air-to-air heat recovery unit was tested with zinc oxide alumina hybrid nanofluid under varying cold and hot air velocities. And finally, copper oxide alumina hybrid nanofluid was tested in a tubular heat exchanger under different flow rates, varying from 3 to 9 LPM. For analyzing heat pipe performance, the equations provided in the slide were employed. Heat transfer rate was calculated by using the first equation, where W, C, and E denote the water, condenser, and evaporator respectively. Besides, eta is the efficiency of the heat pipe. The efficiency of the cold air side of the heat recovery unit was also calculated using the equation at the end of the slide. The overall heat transfer coefficient of the tubular heat exchanger was determined using the equation in this slide, in which in this equation AT represents the total heat transfer area, U is the third overall heat transfer coefficients. T3 and T6 are the inlet and exit temperatures of the hot fluid, whilst T7 and T10 are the inlet and exit temperatures of the cold fluid passage respectively. In this slide, the temperature distributions along the heat pipe wall can be seen. With the utilization of iron copper oxide hybrid nanofluid in a wickless heat pipe, wall temperatures could be declined. Also, a gradual decline was observed in the wall temperature of the heat pipe in the direction from evaporator to the condenser section. The boiling point of the deionized water can also be decreased from 58 Celsius up to 51 Celsius via hybrid nanofluid utilization. The hybrid nanofluid utilization also enhanced the efficiency of the heat pipe under all conditions. The maximum improvements in efficiency was observed under 10 gram per second cooling water mass flow rate as approximately 55%. Efficiency values for the cold air side of the heat recovery units were illustrated in this figure. It's clear in this figure that with the utilization of hybrid nanofluids, cold air side efficiency was able to be enhanced up to 80%. It can be concluded that hybrid nanofluids can be employed in heat exchangers of the air-to-air heat recovery units. And finally, with the utilization of copper oxide alumina hybrid nanofluids, the overall heat transfer coefficient can be enhanced up to 12%. For instance, the overall heat transfer coefficient of the tubular heat exchanger increased from this value to this value when hybrid nanofluid was used in place of deionized water as a working fluid. The increase both in overall heat transfer coefficients and efficiency values result from the upgrading thermophysical properties of the hybrid nanofluid. To sum up briefly, the influences of hybrid nanofluid utilization on the thermal performance of the wickless heat pipe, heat recovery heat, and the tubular heat exchanger were investigated. The aqueous hybrid nanofluid of iron copper oxide, zinc oxide alumina, and copper oxide alumina nanoparticles were prepared and tested in those thermal systems respectively. Temperature distributions along the heat pipe wall can be narrowed with the utilization of hybrid nanofluids, and the efficiency of the heat pipe can be improved. With the usage of hybrid nanofluid in the air-to-air heat recovery units, the increments in efficiency on the cold air side up to 80% were obtained. Furthermore, the overall heat transfer coefficient of the tubular heat exchanger was improved by 12% via hybrid nanofluid utilization. Thank you for attention.
Okay. Dear participants, do you hear me? Okay. Thank you very much, Mr. Çakır. However, Mr. Çakır is not here. So we will go on with Mr. Hazcar Hakkum. Hazcar Hakkum, Mr. Hazcar Hakkum, is you here?
Yes, good morning. everyone.
I am so sorry that for this. Okay, and we will go on about the design and characterization of nickel oxide and zinc oxide heterojection photodetector. Is it okay for you?
Yes.
Okay, I will start the video and after that, if we have a question, please join with us. Okay, and I'm a question that I have to ask you that you give the permission about the recording and broadcasting of your previous presentation for Zoom and the YouTube. Is it okay for you?
Yes, it's okay.
Okay, okay. I will start your presentation. Okay.
Okay.
I will start your presentation. After that, we will join the question section.
Hello everyone, I am Hajar Hakkum. I'm going to give a short presentation on design and characterization of nucleoxide zinc oxide heterojunction photodetector. My presentation is in 4 parts. Firstly, I will tell you a quick background of wide bandgap materials, heterojunction, and development of nucleoxide zinc oxide UV photodiode. Then I will present our proposed idea concerning the research topic. Secondly, what we used as simulation tools, design and characterization conditions. In our work, we are focusing on the behavior of nucleoxide zinc oxide heterojunction interface, particularly the influence of donor and acceptor interface traps densities on the photodiode performance. Thirdly, the results. We found how the acceptor and donor traps affect on the device performance. And finally, conclusion. Let's start. Ultraviolet radiation of sunlight has been known as an important cause of skin cancer. UV protection research has more focus, especially UV devices as photodetectors. Research into these topics create a new optoelectronic generation. Large area, which mean large UV absorption, transparent devices, flexible wearable devices, self-powered help to reduce the size of weight of a system, and wide bandgap materials. The metal oxides or the metal oxide materials are the focus of current research efforts since they are the commonest minerals in the earth. The presented table shows fundamental physical properties of some important metal oxide semiconductors. Tin oxide, also known as stannic oxide, titanium oxide, and zinc oxide has attracted of attention due to the large exciton band in energy, high transmittance and visible range, low tech and low cost, plus zinc oxide still in the trend of UV detection applications. Also, nucleoxide has attracted attention due to the electrochemical stability, low cost, transparency or semi-transparency, and high electrical properties. Nucleoxide and zinc oxide together as a PN heterojunction are good candidates for UV photodetector. Therefore, controlling the behavior of nucleoxide zinc oxide heterojunction improves the device performance. The enhance of device parameters, responsivity, and photocurrent with low technology is the biggest challenge. The interface between these two wide bandgap materials as nucleoxide and zinc oxide still the challenge across a UV photodetector. And our proposed idea comes from this point. Starting that nucleoxide zinc oxide heterostructure design limit its photo detection characteristics. Let's go deeply. Nucleoxide zinc oxide heterojunction interface created by two different materials which causes large barrier beside interface traps. The presence of these traps increases the interface recombination and tunneling current, which gives low photovoltaic effect, which means low photodetection. In short, there is a relation between the nucleoside-zinc oxide interface design and device performance. Our research began from here. Our work followed steps. From the experimental data, we extract some parameters. We wrote a code defining nucleoside as a new material in Silvaco Atlas, designed for design the device, simulate electrical and optical characteristics, and finally to obtain a high-performance device. The following structure describes nucleoside, zinc oxide heterojunction photodetector. As you are seeing, we use gold and FTO as conducting layers. Considering that zinc oxide thickness is 200 nanometer and nucleoside thickness of 100 nanometer. In more details, we have parameters table. The basic parameters we are focusing on are electron affinity and band gap to calculate conduction band discontinuity and valence band discontinuity because they are the important factors to describe the behavior of nucleoside zinc oxide heterojunction. The band gap diagram represents the conduction band and valence band which determine the interface area, where there is the interface traps which are defined as donor-like and acceptor-like traps in this equation. Concerning the physical models, Silvaco used equations Poisson, the continuity of electrons and holes, and transport equations. Considering the recombination statistics. Concerning the UV detection conditions, the wavelength 365 nanometer and light power of 8 microwatt per centimeter. The model used for trap considered as acceptor-like states that are neutral when empty and negative when occupied. Also donor-like, which are neutral when occupied and positive if they are empty. From all these design steps, we get results concerning the influence of acceptor and donor interface traps densities on the electrical and optical characteristics of nucleoside zinc oxide photodiode. Let us look at the first case. The first case was studying the effect of acceptor states of donor on the photodiode performance. Conditions: negligible value donor density. The value of the acceptor trap density was varied from 10 power 7 to 10 power 14. By increasing of acceptor traps, the dark current rises highly at 10 power 14, with noticing the threshold voltage raises. A low dark current density has been achieved at low acceptor trap interface, which is the best choice for low noise application. When there is light, I'd like to focus on this figure. The light current is more affected by acceptor trap density than dark current. Under the high trap states, the device has a poor performance, as we see at 10 power 14. The keywords here: increased interface recombination loses photogenerated carriers. This leads me to my next point: the influence of acceptor trap acceptor states on the responsivity. The responsivity of a photodiode is an electrical current divided by the incident optical power. By looking at this figure, the device detector on the UV region, therefore negligible response on the visible region. The most important note that higher acceptor trap densities gives weak responsivity until the value reaches 30 micrometer per watt. As a primary result, the high-performance acceptor trap states reduce the behavior of the device using recombination process of photo-generated carriers. Let's move on. Another factor. Donor interface trap densities. Following the same steps, the acceptor state has negligible value. The value of the donor trap density was varied from 10 power 8 to 10 power 13. In the absence of light, by increasing the acceptor traps, dark current raises, especially at higher trap density. If there is UV raises, the photocurrent density shows as follows. The light current is more affected by donor trap density. As we see, the donor trap density powerful influencing factor which reduce the device performance at 10 power 13. Now I'd like to move into the influence of donor interface traps on responsivity. The peak of responsivity reduced from 3.5 to 1 microampere per watt due to the high trap densities. These results are a mirror of nucleoxide-dinucleotide heterojunction behavior, which with the presence of acceptor or donor traps. The results help us to understand the trap states in the interface act as recombination centers for the current through the junction. Therefore, controlling the interface trap to avoid these losses and reduce the recombination of photogenerated carriers at the nucleoxide-dinucleotide interface. The existence of traps in metal oxide semiconductor may significantly influence of electrical characteristics of the device. The trap centers influence the density of space charge and semiconductor bulk and recombination statistics. This brings me to the end of my presentation. We have talked about the device has a high performance, low dark current, high photocurrent, besides good responsivity and low interface trap states conditions. After considering the effect of different constituents of the interface trap densities, acceptor and donor states were found that trap states have mainly affected the photodetection of the device due to the recombination of photogenerated carriers. From this work, we confirm that the structural interface of heterojunction properties has a big role to reduce the photodetection of the photodiode by increasing the interface recombination. These results can help many researchers to develop nucleoxide-nucleoxide heterojunction for photovoltaic application. And finally, thank you for your attention.
Okay. Thank you very much. Thank you very much. This wonderful presentation. I will stop your video. And now, dear participants, do you have any question or suggestion to Mrs. Saku?
I have two questions basically.
Okay. Okay, dear professor. Yes, you will ask. Okay.
Initially, heterojunction of nickel oxide and the copper zinc oxide was mentioned, and was mentioned that zinc oxide is p-type and nickel oxide is n-type. That type of thing is there. So my question is how we determine that particular synthesized nanoparticle is n-type or p-type.
Sorry, I didn't understand the question.
No, initially you talked.
Yeah.
And nickel oxide check this whether this material is nanoparticle is basically N-type or P-type. Is there any way to control of this, whether when you are synthesizing you can synthesize P-type or N-type? That is my question.
Actually, when I make here we study just the simulation part. I focused on the device, not on the materials. When I suggest that nucleoxide is as a thin film, it's N-type, and just zinc oxide is N-type. I didn't focus that it's nanoparticle or another.
Okay, you are doing theoretical computations, so you are not synthesizing these materials.
Yes. Actually, in simulation, especially in Atlas, Silvaco, we focus on the device to characterize, make the characterization of the device, not the material, or just we make some parameters of material to define the material. We say like nucleoxide is P-type, it has permittivity, affinity, band gap, this special materials, but we didn't focus on the structure of the material.
Now I understand. Otherwise, controlling the type of the nanostructures is a very tedious task. It's not that easy.
Yes.
So it's fine, but otherwise your presentation is very nice, very good.
Thank you, sir. Thank you, sir.
Mr. Professor, do you have any question to Mrs. Haku? Dear Professor Kumar, do you have any question?
No, nothing.
Okay,
nothing.
okay.
I already asked.
Okay. Thank you very much for your valuable, precious presentation. And the next presentation is also belong to you, Mrs. Haku. Yes, effect of the source solution quantity on the optical characteristic of zinc oxide and nickel oxide thin films grown by spray process for the design nickel oxide, zinc oxide photodetectors. And we will start your video and you have again the permission about the recording and broadcasting of your presentation on Zoom and YouTube. Is it okay for you?
Yes.
Also? Yes. Okay. I will start the video and then we will talk about the questions and suggestions. Okay. Now I will share your presentation in YouTube. Okay. And now we will start your precious presentation video.
Hello everyone, I am Hajar Hakoum. My talk is about the effect of the source solution quantity on the optical characteristics of zinc oxide and nucleoxide thin films growth by spray pyrolysis for the design nucleoxide zinc oxide photodetectors. My presentation is in 4 parts. Firstly, I will begin with quick background about nucleoxide and zinc oxide materials and development of nucleoxide zinc oxide UV photodiode. Then I will present our proposed idea concerning the research topic. Secondly, what we used as an experimental and simulation tools. Thirdly, what we get. And finally, conclusion. Let's start. Ultraviolet radiation of sunlight has been known as an important cause of skin cancer. Recently, UV protection research has more focused, especially UV devices, at the photodetectors. Research into these topics creates new optoelectronic generation, large area transparent devices, flexible photodetectors, self-powered devices. One of the benefits of self-powered is to reduce the size and the weight of a system. They use wide bandgap materials. The metal oxide materials are the focus of current research efforts, and they are the commonest minerals in the earth. The presented table shows the fundamental physical properties of zinc oxide and nickel oxide semiconductors. Recently, zinc oxide has attracted attention due to the large exciton band in energy, high transparency in the visible region, low tech and low cost. Plus, zinc oxide is still the trend of UV detection applications. Also, nickel oxide has attracted attention due to the electrochemical stability, low cost, transparency or semi-transparency, high electrical properties. Nickel oxide and zinc oxide together as a p-n junction are good candidates for UV photodetector. Therefore, controlling the behavior of nickel oxide zinc oxide heterojunction improves device performance. The enhance of two parameters are the responsivity and photocurrent with low technology accuracy is the biggest challenge. The performance of UV detector is mainly dependent on the enhanced characteristics of the semiconductor materials used, and our proposed idea came from this point. Starting with the nickel oxide zinc oxide heterostructure design limit and its photodetection characteristics. Let's go deeply in our idea. Source solution quantity of nickel oxide zinc oxide affect on optical characteristics of nickel oxide and zinc oxide. These optical properties determine the design of nickel oxide zinc oxide photodiode, electrical characteristics, and the optical characteristics, which mean its effect on photovoltaic effect and photodetection. In short, there is a relation between the material's properties and the device performance. Our research began from here. Our work followed steps. We did the growth of nickel oxide and zinc oxide in films. From the experimental data, we extract optical parameters. We wrote a code and defined nickel oxide as a new material in Silvaco Atlas decade. To design the device, simulate electrical and optical characteristics, and finally to obtain high-performance device. Experimental details in this work by spray pyrolysis method nickel oxide films growth on glass substrate with condition primary product, concentration, temperature, and it's for 3 different quantities of solution, 5, 10, and 15. Also, we did the growth for zinc oxide with the following conditions. Then, we did the optical characterization to extract optical parameters used in simulation section. Let's move on to simulation conditions. The following structure describes the nickel oxide zinc oxide heterojunction photodetector. As you are seeing, we use gold and ITO as the conducting layers. In more details, we have parameters table. The basic parameters we are focusing on extracted band gap. We use Silvaco Atlas decade for our simulation. Physical models used in Silvaco Poisson equations, the continuity equations, and transfer equations. Considering recombination statistics. Concerning the UV detection conditions, the wavelength 365 nanometer and light power of 8 milliwatt per centimeter to simulate the electrical and optical characteristics. Let's move on to experimental results section. In our study, we focusing on the optical characterization. Nickel oxide shows high transmittance in the visible range when it reaches 79%. Nickel oxide 5 and nickel oxide 10 do not show a big difference, while nickel oxide 15 shows a dropping of transmittance. We're decreasing by 18% comparing with to nickel oxide 5 and nickel oxide 10 in films. The absorption of nickel oxide films decrease with wavelength increases. In other words, nickel oxide shows high absorption in UV range, and the absorption increase with the increase in the quantity of solution. Zinc oxide shows high transparency in the visible range too. The average transmission value is over 85% for zinc oxide 5 and zinc oxide 10, approximately equal, and decreases by 9% for zinc oxide 15. The absorption increases in the UV range, which confirms the increase in the thickness. From this optical measurement, we extract band gap of nickel oxide and zinc oxide. As you see, the band gap of nickel oxide decreases as the quantity of solution increases from 3.6 to 3.5 electron volt. For the zinc oxide films, the increases quantity of solution, there is negligible increase of the optical band gap. The extracted parameters of nickel oxide and zinc oxide thin films used in simulation are thickness, optical parameters, as we said, band gap, refractive index, and injection coefficient for all deposited thin films. Our simulation divided into 3 parts. Simulate device at different solution quantity of zinc oxide. Second, different nickel oxide solution quantity. In this presentation, we will talk about the third one, different solution quantity of nickel oxide and zinc oxide together. As we see in the following graph, the variation of the current voltage characteristics under dark and illumination as a function of the quantities of solution of the two materials together, nickel oxide and zinc oxide. The first observation is the dark current is increasing by increasing the quantity of solution. In contrast, the photocurrent increased by increasing the quantity of solution. And we can see that the threshold voltage is decreasing. The responsivity. The responsivity of a photodetector is an electrical current divided by the incident optical power. By looking at this figure, the device detects on the UV region, therefore negligible response on the visible region. It has been observed that the quantity of solution of zinc oxide and nickel oxide layers increase, the responsivity also increase. The peak of responsivity increased from 0.09 to 0.14 ampere per watt. The results help us to understand optical characterization of nickel oxide and zinc oxide depend on the quantity of solution conditions, with the high optical characteristics making them suitable for optoelectronic application. The optimum quantity of solution for the design of good photodiode performance is 15 milliliter for zinc oxide and nickel oxide together, due to lower dark current and high photocurrent plus high responsivity. Finally, the conclusion. Zinc oxide and nickel oxide thin films were prepared using the spray pyrolysis technique using 3 different quantities of solution, 5, 10, and 15 milliliter. The different optical parameters obtained for both films are then used to simulate the electrical characteristics and responsivity of a nickel oxide zinc oxide heterojunction-based PN photodiode. Both the electrical characteristics and the responsivity improve with increasing quantities of solution. From this work, we confirm that the optical characteristics of thin films used for design of photodetector have a big role to enhance the photodetection of the device by increasing the quantity of thin film. The obtained results may help many researchers to develop nucleoside dinucleoside heterojunction for photovoltaic application. From here, we finish our presentation. Thank you for your attention.
Okay, thank you very much, Mrs. Hakkı. This is very nice presentation for photodetectors. I congratulate you. And is there any question about this wonderful presentation?
Yes, can you hear me?
Yes, I hear you. And you can ask your question to Mr. Hakkı, Mrs. Hakkı.
Mrs. Hakkım, thanks your good presentation. I am interested in your materials design. And I want to ask, how do you prefer? How do you prepare your layer by layer films with spray pyrolysis? These are the layer by layer or other composite materials?
You talk about the heterojunction or just the thin film? When you ask me about the materials, the deposition of thin film or the deposition of heterojunction?
So we can say, yeah. So can we say, you produced first nickel oxide layer, and then you deposited the zinc oxide layer. Is it true?
Here, I just make the deposition of thin films, not the heterojunction.
Can we say
I make the deposition of zinc oxide film and in another substrate? I didn't make a heterojunction. I just make the thin films and make characterization for them, extract parameters, and input them in the simulation, not the heterojunction.
Okay, so can we say these are the separate materials, or did you use them together?
It's separate materials. No, it's separate.
It's separate.
Thin film in one substrate and zinc oxide in another substrate.
Another substrate, nickel oxide.
Yes.
Can you try to together them?
I make them together and I make the characterization for them. Actually, I have a heterojunction.
Okay,
thank you. Too.
Thank you so much.
Okay, thank you.
Thank you very much. Thank you very much for your nice presentation, Mrs. Hakkı. Is there any question about these two presentations belong to Hakkı, Mrs. Hakkı? Is there any question? Okay, let's go on. The next presentation is belong to Mr. Berkcan Erenler. Berkcan Erenler is our students in Gazi University, at Gazi University Photonuclear Research and Application Center. He's an expert and is our student. He prepared a wonderful presentation about the structural and optical properties of radio frequency magnetron sputtered indium sulfide thin films. Okay, Berkcan, did you hear me?
Yes, sir.
Okay, I will ask to you that I have to ask you that do you have giving the permission about the recording and broadcasting of your presentation video to Zoom and YouTube? Is it okay for you?
Okay, sir.
Okay, let's go on about your video, and then please join us with the question and the suggestion section. Okay.
Thank you, sir.
Okay, I will share your video firstly, and then we will talk about question section. Okay. Now I start your presentation.
Hi, I am Berkcan Erenler. I am master student, Gazi University Metallurgy and Material Engineering. And I'm working Photonics Application and Resource Center. And my thesis, I continue my thesis work in this center. Our work, structural and optical properties of RF magnetron sputtered indium sulfide timbrings. Our team Neslihan Akçay, Yunus Özen, and Professor Dr. Süleyman Özçelik. Supervisors, Professor Dr. Süleyman Özçelik and Professor Dr. Hakan Ateş. Outline, introduction, experimental, and then characterization, and then conclusion. Indium sulfide has an N-type semiconductor with wide range band gap, 2.0 3.4 electrovolts. Indium sulfide has a chemical stability and non-toxicity is very important for solar cells. High photoconductivity, high transparency in the visible spectral region as an alternative buffer layer to cadmium sulfide in thin film photovoltaic applications. We choose RF magnetron sputtering technique, and this reason I want to explain this method clearly. Magnetron sputtering coating is a vacuum coating process that falls under the category of physical vapor deposition and is mainly used for depositing metals, alloys, and compound textiles and other materials. Figure 1, you can see schematic illustration of the co-sputtering system. This system belongs to Photonic Application Research Center.
I would like to welcome
I'm sorry that there is a problem, Berkcan. I'm sorry. I will start again the presentation. I'm so sorry. Okay. And maybe more helpful for listener. And we will start again, and then we will go on about the presentation questions.
Hi, I am Berkcan Erenler. I am master student, Gazi University, Metallurgy and Material Engineering. And I am working Photonics Application and Research Center. And my thesis, I continue my thesis work in this center. Our work, structural and optical properties of RF magnetron sputtered indium sulfide timbrings. Our team Neslihan Akçay, Yunus Özen, and Professor Dr. Süleyman Özçelik. Supervisors, Professor Dr. Süleyman Özçelik and Professor Dr. Hakan Ateş. Outline, introduction, experimental, and then characterization, and then conclusion. Indium sulfide has an N-type semiconductor with wide range band gap, 2.0 3.4 electrovolts. Indium sulfide has a chemical stability and non-toxicity is very important for solar cells. High photoconductivity, high transparency in the visible spectral region as an alternative buffer layer to cadmium sulfide in thin film photovoltaic applications. We choose RF magnetron sputtering technique, and this reason I want to explain this method clearly. Magnetron sputtering coating is a vacuum coating process that falls under the category of physical vapor deposition and is mainly used for depositing metals, alloys, and compound textiles and other materials. Figure 1, you can see schematic illustration of the co-sputtering system. This system belongs to Photonic Application Research Center. A target that desired to be deposited is bombarded with energetic ions of inert argon gas. We use argon gas, this process. The forceful collision of these energetic ions with the target ejects target indium and sulfur atoms into the space. These indium and sulfur atoms are then deposited on the substrate material, forming a indium sulfide thin film. In this process, substrate, soda lime glass, and silicon, power 13 watt IF, and substrate temperature 150 Celsius, argon gas pressures 10 millitorr, base pressure 10 to power of -7 millitorr, flow rate 4.3 ccm. Characterization: the thickness of ground films on soda lime glass and silicon substrate were found to be 35 nanometers and 60 nanometers by profilament measurement, respectively. Characterization: X-ray diffraction method. X-ray patterns show that the films deposited on silicon had a tetragonal structure. You can see figure 3. And no peaks were seen in the X-ray patterns of the films deposited on the soda lime glass. You can see also you can see figure 2. Fourier transform infrared spectroscopy, FTR. Also, you can see figure 4. The absorption peak centered at 1371 and 798 were attributed to indium-sulfur vibration modes of indium sulfide. In addition, two absorption peaks at 1110 and 610.5 originating from silicon substrate were also observed in this spectrum. These results are compatible with previous studies and UV visible spectroscopy. The energy band gap values of the ground films were calculated by Tauc plot method and determined as 3.1 electrovolt, which is consistent with the value obtained by Razulel. From the UV visible spectroscopy analyses, it was seen that the films had average transparency 60 in 400, 850 nanometer region. Conclusion is a final part. The thickness of the ground films on soda lime glass and silicon substrates were found to be 35 nanometer and 60 nanometer by profilament measurements respectively. X-ray patterns show that the film deposited on silicon had a tetragonal structure. No peaks were seen in the X-ray patterns of the film deposited on the CRG. In FTR spectra, these peaks fingerprints also are structure we determined indium sulfide thin films. And also the energy band gap values the ground films we determined 3.1 electrovolt. Obtained results show that deposited indium sulfide films can be used buffer layer to CTS thin film cells with casterite absorber layer. References. And this work is supported by Presidency of Turkey, President Strategy and Badish with project number, and this project belongs to TÜBİTAK Thank you all.
Okay. Thank you very much, Mr. Erenler, for your wonderful presentation. Thank you very much. Is there any question or suggestion about this nice presentation belong to Mr. Erenler? Is there any question? Okay, Mr. Erenler, I have two maybe technical question. Your results are also very good. I have two technical question about the process. Okay, this question first is why you say that the argon gas we use in the sputtering system. Why we use argon gases, and the argon gas is not introduced the thin film, or it can be introduced the thin film. What's your opinion about this?
It's cheaper than helium. First reason. And commonly use the argon. I don't know why.
Okay, maybe you will learn why we use the argon gas. Okay, we will talk about these argon gas uses later. And the second question about the soda lime glass. You said that we cannot see the XRD peaks on the soda lime glass. Do you have the opinion why we cannot see the XRD peaks on the soda lime glasses?
First, indium sulfur thin films on SLG thinner than indium sulfur film on silicon. I think is first reason.
Yes.
Maybe this material not crystallize, or we have not grazing indigenous XRD measurement system. Maybe reason is.
Yes, it can be possible.
Or so the lime
yes.
glass is amorph.
Yes.
Is third reason.
Yes, yes. Maybe the main reason about the XRD graph, XRD measurements on the amorphous structure cannot be seen easily in the XRD measurements. It can be possible. Okay. Thank you very much for your nice presentation. I wonder about is there any question about this presentation?
Yes, actually, dear chair, may I connect your session?
Yes, of
because
I'm so sorry, Professor Ateş, that you have opened another video in your computer. The noise is so much.
Voice so much?
Yes. In the YouTube, I think YouTube channels voice. Okay. Professor Ateş, can you hear me? I don't hear you. Now I can hear you. Is there any question to your student?
You can my voice.
Yes.
Actually, I have lots of questions to the background analysis. But firstly, I would like to thank Dr. Tarık Asar to this good chair. I would like to thank Professor Süleyman Özçelik, support us every time in botanic laboratory. I would like to thank Berkcan Erenler, my student, our student, very successful student. when he started this kind of the studies, I was be happy because very huge people. Can you tell me, Berkcan, after this explanation, can you tell me about your study? What is the new challenge of your material and technique? Very little bit.
Commonly, indium sulfide synthesis commonly use chemical bed deposition or another techniques. We want to use magnetron sputtering technique because it's a physical method. You know, sometimes physical methods better than chemical methods. We want the physical method, physical vapor deposition, magnetron sputtering is the reason.
Actually, you mentioned the material and the technique
Yes.
have a very big challenge near future, especially producing the films and other type of the material. Thank you. Aside from this, I would like to thank all of the participants in your session and Tarık, Dr. Tarık. Thank you.
Thank you very much. Thank you very much. Okay, this is the last presentation. We have another presentation, but the presenter is not here. So this is the last presentation with Mr. Erenler. We can close the section, but I want to thank to Professor Ateş and their colleagues who helped to presentations, organizations, and etc. We have a big group background this video conference, and thank all organizing committee. And also thank to Professor Ateş. And if you haven't got any question, I want to close the section, morning section at Ankara Hall, the first section of this day. Thank you very much for your participants and precious questions and suggestions to presenters. Thank you very much. Thank you very much for your all. Okay. I hope in the next years we will see again this conference, the next conferences. Thank you for your all. Okay, Professor, I close the section and all participants. Thank you very much again.
Thank you, Tarık, and thank you all participants.
Thank you very much.